Hi, I'm Mika Lan from the team Blackpink in your area, and in this video, I will be sharing with you my learning journey on the theory, design, fabrication, and flight testing of my remote-controlled plane, Lalisa Mark-VII. My design objective is to create a slow-flying plane using proper engineering design tools. The name of my plane is called Lalisa, and this is Mark V and Mark VII. In between, I've made some enhancements. The design of my plane starts on the lift equation. There are 5 parameters: lift, which is equals to the weight of the plane, the lift coefficient, air density, velocity, and wing surface area. Since I want a slow flying plane, I rearranged the equation for V. To reduce V, there are 4 ways to do it. First is to create a large lift surface area, a large lift coefficient in reference to wing foil and wing design, a light weight, and fly the plane at high air density. There are 2 main designs, a tube and wing design versus a blended wing body design. Given the same volume, a blended wing body design has a larger lift surface area, so it is more efficient aerodynamically. Therefore, I choose to use a blended wing body design. The airfoil design is a trade-off between lift and drag. I choose to use a low-speed airfoil to generate more lift at the expense of drag. As a result, the plane will fly slower, which is in line with my design objective. I use a delta wing design because of the additional vortex lift. Vortex starts perpendicular to the sweeping edge of the wing. It traps the high-speed spinning air on the top of the wing, creating a low-pressure zone on the top of the wing, sucking the plane up. The high-energy vortex delays the airflow separation on the top of the wing, allowing the plane to fly at high alpha. There is a trade-off between the design of the plane and the weight of the plane. If I were to design a structured plane, there would be some overhead of the weight of the structure. Therefore, I make sure that given the weight, I can fully utilize the wing area. Because the hoop size in the challenge is 150 cm by 150 cm, I designed the wingspan to be 60 cm to give a reasonable clearance. Cold air has higher density than hot air, so it is preferable to fly the plane in cold conditions, for example, in air conditioning rather than outdoors. However, this is outside my design control. In conclusion, my design strategy for a slow-flying plane is to use a blended wing body design with a wingspan of 60 cm, and a low-speed airfoil and a delta wing design, and create the plane as light as possible given the structure, and fly the plane in cold conditions. This is a time-lapse of me designing the plane on Autodesk Fusion 360. And this is my fabrication process. Theoretically, we calculated the center of gravity to be over here. But during the fabrication of this model, there may be some plus or minus. So we need to refine the position of the center of gravity, which we estimate to be somewhere around here. To do this, we need to perform a glide test, because if this plane can glide, it gives me confidence that it can fly. So let's do it. Roll, pitch, and yaw are controlled by a control surface, which requires airflow to work. Airflow depends on the speed of the plane, which is a function of time. Therefore, the flight path of the plane will trace out a 2-dimensional surface as it flies through the air in time. Actually, the flight path is not a true 3-dimensional movement. the plane is moving on a two-dimensional surface in a three-dimensional space. In flying a plane, we are designing a two-dimensional flight path for the plane to travel on. This is the end of my sharing of my learning journey. I hope you have enjoyed it. Thank you.